Hello, welcome to Astronomy on Tap Virtual Edition Volume 2. I'll be your host for this evening. My name is Joe Burchett. I'm a postdoc at the UC Santa Cruz, at least for 3 weeks, 3 more weeks, or maybe another hour and a half, depending on how all this goes. But we have a wonderful program for you tonight. Please sit back, enjoy a tasty beverage, and learn about some fascinating astronomy. We have a couple of talks from Dr. Kyle Westfall and Dr. Nicole Drakos, a couple of scientists at the UC Santa Cruz who are going to talk to us about motion in the universe and maybe what it can tell us about dark matter and galaxies themselves, among other things. So I know what you're thinking. Where the hell's Alexa? Can we just have her back? Well, Alexa is moving on to greener pastures, but we did convince her to come on by one last time to say hello. So Alexa, if you would please go ahead and turn on your video.
Hi.
Hey, Alexa, how are you been?
Oh, doing all right. It's exciting time, but I don't recommend trying to move during a pandemic. It's a little tricky, but it's good.
Yeah, so most everyone knows Alexa has been the face of Astronomy on Tap Santa Cruz now for years. You started as MC all the way back in our New Bohemia days, and you've been with us since through the move to Santa Cruz Mountain Brewery. And then you were MC, of course, for our first virtual edition. So you will now, as I alluded, we'll be moving on to greener pastures. So can you tell us a little bit about your new position, sort of what's in store for you?
Yeah, so I am going to be moving to Ontario, Canada, to start a research position at the University of Waterloo Center for Astrophysics. And so I'm going to be working on pushing how we can get and uncover better and better fossil evidence of the earliest star formation epochs in the universe, and how that can inform, where we all came from and why we get the stars we get, and how galaxies come together in the end. So I'm really looking forward to being in just a really exciting community and talking to new people, and yeah, so it'll be great. I just have to get across the border first, which is a little trickier than it would be otherwise.
Yeah, I understand it's quite a challenge at the current moment. But once you get there, I'm sure you have just lots of...
An interesting little challenge is I can't rent a U-Haul truck to drive to Canada because I wouldn't be able to return it upon arrival, because that would be breaking quarantine. So that's I've been dealing with a lot of little logistical issues, but it's all for the point of understanding space and understanding science. And hopefully I'll come back in a year and the pandemic will be over and I'll be able to give an AOT talk here about my amazing new things I've discovered in Canada.
We'd absolutely love that. And I say I mean, Astronomy on Tap Santa Cruz, I myself will be moving on as well, but no, this is great, and I can't say that I envy you on those logistical, what sounds like a kind of a headache and a half, just figuring out all that. But once you get there, once you get settled, I know it's going to be awesome, and they are better for having you. And yeah, just from all of us here at Santa Cruz, thank you so much for all the great times. Astronomy on Tap has been an absolute blast, and you've really made it that way. So thank you, and goodbye for now, but hopefully not for long.
Well, thank you so much. It's nice to be invited on for this little goodbye. I've loved Astronomy on Tap. I loved the people I was able to meet through it and work with through it, and so very proud of what we did here. And so I look forward to see what the new generation of people do with it.
Absolutely. Absolutely.
So
well, thanks again.
Sorry.
Go ahead.
I was just going to say, I'll let you move on to the show, the main event. I don't want to keep you too long.
Great. Well, thanks again for coming by, and best of luck on everything, and hope you get across that border and with or without a U-Haul.
Thank you. Bye.
Bye. Okay, so it's been an exciting time here in the last few weeks since we last came at you, and I wanted to talk about just a couple of the exciting things in the news. Perhaps one of the most exciting is actually some astronomy we all can kind of take part in, and that is the appearance of the comet NEOWISE. So, as you may or may not know, tonight, July 23rd. Comet NEOWISE is on its closest approach to Earth. So we can go out and check out Comet NEOWISE. This is I believe it's the first naked eye comet that is a comet you could go out and see with your naked eyes since Hale-Bopp, which I remember from the late 90s. And this is not going to be quite as bright as Hale-Bopp, but it should be nevertheless a rare phenomenon we get to take part in here. And so to go out, please do go out and check it. Look for it in the night sky after Astronomy on Tap, of course. So this is just a little guide of how you could spot NEOWISE. So if you look about an hour and a half after sunset to the northwest, and if you can spot the Big Dipper, you should be able to find NEOWISE. So this is just a little sketch here. You see the stars of the Big Dipper, and we have just the days of the month in July. Today's July 23rd, so we should be able to see NEOWISE just following the bowl of the Big Dipper just down towards the horizon. So check it out. If you have a pair of binoculars, you don't even need a pair of fancy binoculars. Be sure and take those out because you should be able to see even more of the tail, maybe even two of the two tails, one of which is a sort of thinner tail of dust streaming off the comet, pointing directly away from the sun, and the other is a sort of fuzzier, broader tail that you can see here. This is ionized plasma that's being ejected from the comet itself. So yeah, check that out, because if you don't, you're going to have to wait 6,800 years, and I have a feeling that not a lot of us will be around to see it on its return pass. So please do check that out. Okay, and now in other news, we've had the first image of exoplanets, the direct image, picture taken of exoplanets around another sun-like star. Now, this is not the first direct image of exoplanets. There have been others, but this is the first one around a star like the sun. So the phone number of the star is TYC -8998-760-1. It's not important, but what is important is these two objects here, seen in this observation with the very large telescope down in the southern hemisphere. So these planets, I want to point out, are much more massive. They're gas giants, but they're much more massive than a couple of our gas giants we know and love here in our own solar system, namely Jupiter and Saturn. 14 times the mass of Jupiter and 6 times the mass of Jupiter, respectively, for these two objects. And lastly, this is a very different kind of planetary system, not only in its mass, but these planets are going to be found much further out, separated from their star, than Jupiter and Saturn from our own star. So the orbits are about 32 times the radii of the orbits of Jupiter and Saturn. So this just really speaks to sort of the types of systems we're able to directly image and characterize with current facilities. So this is really part of what makes this observation possible, is they're well separated from their host star. And I'll just say, please stay tuned. There's lots more of exciting work detecting, imaging, characterizing exoplanets right from many of the faculty right here at UC Santa Cruz, especially from the Other Worlds Laboratory. Just in terms of a research group, this logo just can't be stopped. It's amazing. But Rebecca Jensen-Clem, Andy Schemer, and Emily Martin are all three leading programs, observational initiatives that were recently funded by the Helsing-Simons Foundation. And so stay tuned for lots of great science coming from that group at UCSC. Okay, so getting on to our talks for this evening. Our first up, we have Dr. Kyle Westfall. Hello, Kyle.
Hello.
How are you this evening?
Good. How are you?
Great, great, great. So Kyle is a research scientist at UC Santa Cruz, UC Observatories. And you're going to be talking to us about motions and galaxies tonight.
That's right.
Yeah, so let's go ahead and see what you got to say. Everybody, please, as I said, relax, sit back, enjoy the ride. If you would, go ahead and post any questions you have right there in the YouTube live chat. We'll be collecting those, and at the end of the talk, we'll hear directly from Kyle, and he can answer whatever questions we have. And also, you can post any questions to or comments, pictures of your animals to Instagram, Twitter. We'll be providing those handles on the YouTube live chat as well. So join the conversation, enjoy, and take it away, Kyle.
All right. Thanks, Joe. So tonight I'm going to tell you a few things that we know about how galaxies move internally and with respect to one another. So I wanted to start out with this simulation of a Milky Way-like galaxy. So this is a simulation of a galaxy that we think is similar to our own galaxy that we live in. So the simulation starts with the galaxy being very smooth, and then you see it evolve over time to show us things like spiral structure and density waves and things like that we think that exist in our own galaxy. But of course, this is much sped up compared to what we actually see in the universe. And so I wanted to kind of start by putting some of the timescales and distances into context. So and how that affects how we observe galaxies in the universe. So the universe is filled with galaxies. There's lots of opportunities to observe them at different stages in their lifetime. And so the question that I want to address tonight is, how do they move and how do we measure it? So like I said, let's start with the Milky Way. It provides us a unique perspective because we live inside it that has advantages and disadvantages, but I'll start there because that's our home. And so if you could somehow get outside of the Milky Way and look at it from the face on, this is an artistic impression of what that might look like. So here's the center of the galaxy. We think we live in a barred galaxy, so there's an elongated structure in the center of the galaxy. And then our sun lives about 8 kiloparsecs from the center. That kiloparsec is a term that you'll hear a lot in astronomy. It's just a measure of distance. So how does our galaxy move? Well, we can measure that a little bit more easily than in other galaxies. And so if you just make a plot of what we call the Milky Way rotation curve, which is its rotation speed on the y-axis as a function of its distance from the center, it looks like this. The data are here in triangles and circles from a compilation of different observations by this review paper. And this point here is our sun at about 8 kiloparsecs from the center. And you'll notice that this distance axis here is again in kiloparsec, which is an absurd number of miles. And so that's where we use kiloparsecs, because it's miles just as an irrelevant metric on this scale. So we see that the sun rotates at about 200 kilometers per second. So again, to kind of put that in more terrestrial terms, that's crazy. That's 450,000 miles per hour. And so if you were actually to move that at that speed, you could circle the Earth in less than 4 minutes. And just to give you some context there, it's one of the fastest man-made things that sits in orbit around the Earth is the International Space Station, which takes about 90 minutes. So you're going much, much faster than that. So things seem to be moving very, very quickly. But we're talking about really, really large distances here. So what, again, to kind of put this into context, at the orbit of our sun, where our sun orbits around the center of the Milky Way, it actually takes the sun about 240 million years for it to move that distance, just because it's such a huge distance, even though we're going as fast as I said. So again, to put that into context, the first dinosaurs showed up on Earth at about that time. So we've gone basically once around the galaxy in the time that the first dinosaurs showed up on Earth. And if you count back to when they went extinct, we've gone about a quarter a turn around the Milky Way in that time. And if you think about all the time that humans have been on the Earth, it's been about 100,000 years. We've only moved that much, this very small amount, less than 1 degree around the center of the Milky Way. So if things take so long to see motion on the sky, how do astronomers actually measure how galaxies move? So to explain that, I'm going to open up two bits of the astronomer's toolbox. The first one is on atomic transitions. So a very amazing property of atoms is that they can only exist in very specific energy states. And transitions between those energy states result in light being emitted. And so, for example, if you take the electron in the hydrogen atom from its n equals 3 state to its n equals 2 state, it emits a photon that sits at 656 nanometers. And you can measure this in the lab. So this is a lab spectrum where you've taken a hydrogen gas, you've heated it up so that it's in an excited state, so that it emits photons, and then you use a little grating and you look through it, and this is what you'll see. You'll see that emission from what we call H alpha, and then for a different transition, we call it H beta, H gamma, H delta, etc. And so this basically forms a fingerprint that we can use to, one, understand what galaxies are made of, but two, also have a reference frame for what frequencies that light is being emitted in the galaxy itself. And so we can see that in galaxies. This is a spectrum of a galaxy taken from a survey that I'll talk a little bit more about later. And you see these lines. You see the H alpha line, H beta, H gamma, H delta. And the reason that we know that these lines are from hydrogen is because of that fingerprint, because of this very specific pattern that they appear in the spectrum. But hydrogen, of course, isn't the only element that you see in galaxies. You see oxygen, neon, helium, nitrogen, sulfur, lots of different elements. And we use all of those elements together to understand the frequencies of light that are being emitted from the galaxy. So the second principle is called the Doppler effect. And this is basically telling you how those frequencies are changed given motion between you and the thing that you're looking at. So here's just a couple things that I pulled off of Wikipedia. So on the left plot, nothing is moving. It's emitting waves at a certain frequency, and it doesn't matter where you are around that object, because it's not moving with respect to you. You always see the same frequency. But on the right, the object is moving. And so if you were an observer sitting here to the right of this object, you would see the frequencies it was emitting being increased, or its wavelength being decreased. And the opposite would be true if you were sitting on the left side of the image. So we can use, one, the fingerprint that the atomic structure provides, and then the difference between what we know the frequencies should be to ascertain motion, or to infer motion. So let's take these two principles and try it out. So I just picked these two galaxies from a survey that, again, I'll talk a little bit more about later. We can take a spectrum of each of them, and then we can look at and try to find those lines from atoms being emitted in the galaxies. And this is what you see for these two galaxies. So if I just take what we know from lab experiments for where these lines should be, H alpha should be here, nitrogen 2 should be at these two positions, and sulfur 2 should be at these two positions. But in the observed spectrum, you see they're shifted. So for this galaxy, they're shifted by about 3%. We use this term called Z or redshift to describe this measurement. So the shift of about 3% is what we see for this galaxy. And for this galaxy, the shift is more like 11%. And what that means, or what that would mean, is that this galaxy is moving away from us. They're both moving away from us, but this one is moving much faster than this other one. So we can do this now for millions of galaxies, and it has been done with many different surveys, but one of the most extensive surveys has been the Sloan Digital Sky Survey. And it's observed millions of galaxies over the northern sky and mapped out their redshift as a function of position, which is what's being shown here on the right. So if you just plot galaxies as individual points, given their direction on the sky, that's what this circle represents. And the distance within the circle is represented by their redshift, their Doppler shift. And what we find is basically all galaxies show redshift. There are very few galaxies that have a blue shift that look like they're moving toward us. And this is one of the first evidences that we had that the universe is expanding. All galaxies are moving away from every other galaxy. But I'm going to do that typical physicist thing or scientist thing and tell you something and then tell you why it's wrong in detail, which is that, I said that Doppler shifts infer motion, but in fact, what we're seeing here is we're not seeing motions between galaxies, but we're seeing the expansion of space itself. And this was, like I said, one of the first evidences that the universe is expanding. And these plots like this are really interesting because they show us basically how how galaxies are situated in the universe, and the very detailed structure that pops out of that, which we call the cosmic web. And I'll just highlight this video that's recently gone up from the Sloan Digital Sky Survey from its most recent compilation of data like this. But you can use the same principles that I talked about to actually infer motions within galaxies. So instead of looking at two galaxies and telling how they're, what the Doppler shift is relative between the two, you can actually look at different positions on a single galaxy and you use the same technique. You look at lines, you measure their shift with respect to what we know they should be, and you can do that all over the face of the galaxy, and you get an image like this, where you see on one side of the galaxy, it looks like it's moving away from the center, and on the other side, it's moving towards us with respect to the center. And we can do this for thousands of galaxies, and that's the survey that I've been alluding to throughout this talk, which we call MANGA. It's one of the phases of the Sloan Digital Sky Survey that took many of these different what we call integral field units and put them on thousands of galaxies to measure things like their internal motion. So one question we can ask is, do galaxies rotate like our own galaxy? So we can do this with MANGA. Here's a galaxy for one of the galaxies in the survey. We've measured its motion with respect to the center, and then we've modeled that with a very simple rotating disk model. And if you fit the data with that model, then you can plot exactly what I showed before, but for this galaxy as opposed to the Milky Way, which is the rotation speed on the y-axis and the distance from the center on the x-axis. And we can make this measurement both for different components of the galaxy as well, so for the gas and for the stars, and you see that they rotate differently. But in general, when we see curves like this, where much of the galaxy is rotating in a systematic way, we call that ordered motion. It's on the galaxy as a whole is rotating. There's not much deviations about that rotation, which is similar to what we see in the Milky Way. But galaxies look very different. Not all galaxies look like our Milky Way. Some of them look like fuzzballs, whereas others show a structure that looks more like our Milky Way with spiral arms in that. So one question we can ask with MANGA using these internal motion measurements is, do all galaxies rotate? Or do the differences in the way they look indicate some differences in how they move as well? So just to remind you of how we classify some galaxies, these things here on the left we call ellipticals, these things on the right we call spirals, and then there's groups that are in between those two. One that look like they might be transition objects, and then others where they just look like a mess. We'll call them irregulars. So we can construct plots like this, and this is a bit messy, but I'll take a second to go through it. Basically what this plot is telling you is, on the y-axis we're showing whether the galaxy has ordered motion, so things that are rotating like a disk, or whether they're dominated by random motion. So there is no single direction where most of the stars are moving. They're kind of all moving in a variety of different directions. And on the x-axis, you plot what the shape of the galaxy look like. Does it look like a circle, or does it look elongated like an ellipse? And what this shows is that galaxies that look different actually do have different motions. They do exhibit different properties in their in what we call kinematics. So the things that look like spirals, that look like our Milky Way, mostly are rotating. They mostly do have they are dominated by that ordered motion. Whereas things that are more circular or more elliptical, these red points here, they have more random motions associated with them. And all of this is to try to understand how galaxies got this way. Are there transitions between different galaxies, and try to understand where they will go in the future? Like, what will the ultimate state of our Milky Way galaxy be in billions of years? So I hope that gave you a flavor of how astronomers make these measurements, what are the limitations, and some of the kind of big discoveries that have come out of that. And I will end there. Thanks so much for attending and for listening.
Okay, very cool stuff there. So yeah, just a reminder to everyone, please go ahead and put any questions you may have into the YouTube live chat. Hit us on Facebook, Twitter, or Instagram. You can find those handles there in the YouTube chat. Yeah, very awesome stuff. Because so if I could just take the MC's executive privilege here and ask the first question. So you were talking about mapping out and sort of revealing the cosmic web in this structure of the galaxies, and mapping the galaxies, finding their redshifts. And so recently, I know that the Sloan Digital Sky Survey released, and then you actually showed a graphic from their new data release where they've pushed out to further and further distances from Earth, how basically finding different classes of galaxies. And so I was just wondering if you could comment on that a little bit, maybe tell us sort of what the step forward was in this recent data release, and maybe just to talk a little bit about kind of what we've learned through mapping the cosmic web in this way.
That's a great question. I'm probably not going to do it as good a service as I should be able to. I'm mostly familiar with the MONGA survey, but I'll just say that. So you're right. So Sloan Digital Sky Survey has been around for a while. It's been around for about 20 years now. And its initial mission, part of its initial mission statement was to do exactly what that plot showed, which is to look at the distribution of galaxies across the sky and how they spread out in redshift. And just to make the connection that it didn't quite make in the talk is that another very fundamental thing that we learned way back in the 20s and 30s was that a galaxy's motion with respect to us is correlated with its distance. So the higher its redshift, the further it is away from us, and that goes along with this idea of the universe expanding, and that's why all galaxies are moving away from us. And so when you hear astronomers talk about redshift, they use those terms interchangeably, redshift and distance. And so it's always interesting to push to higher redshift because that pushes to larger distances, which, given the way that light works, is actually pushing further and further back in time. So that's one connection. So that plot that I showed earlier, if you remember, the redshift axis went out to about 0.15, and so that's saying that there's about a 15% difference in how where the light is emitted versus how we observe it. And more recent releases have pushed out to redshifts of 1. So that's 100% change in the frequency of the light that we observe compared to how it was emitted. Now, one of the reasons, of course, to push out further, like I said, is to get for further distances, but you want to see as well how that structure that we saw in that image changed as a function of distance, as a function of time through the universe. You can see how the structure of the separation between galaxies, the structures that galaxies form, how that changed as a function of time. And so the Sloan Digital Sky Survey, and particularly its most recent survey along this line, which is called the Extended Baryonic Acoustic Spectroscopic Survey, EBOS. It's looking for those changes in the structure of how galaxies situate themselves as a function of time, and that tells you effectively a lot about the universe itself and how different fluctuations in the universe led to galaxies that we see today. So that was a very long-winded answer to your question, but I hope that covered a few things.
No, I think it speaks to all of the science that can come out of these kinds of surveys, and just how we can learn about cosmology, we can learn about the evolution of galaxies themselves. It's and all of the myriad questions in both of those sort of subfields. So no, that's great. That's great. And so I think one clarification. So we had a question come across the YouTube live chat. Is redshift correlated with speed or with distance or both? So I think you came across this, but maybe just to kind of spell that out.
Yeah. So this is where I had to do the thing of you explain a concept and explain why the interpretation of that concept is wrong in some cases. And so particularly when you're talking about redshift of galaxies, it's important to understand that some of that motion is motion of galaxies with respect to one another. For example, the Milky Way is moving toward its nearest galactic neighbor, or nearest, of order the same mass galactic neighbor, the Andromeda galaxy. We're moving toward that. And the reason for that is because of gravity. And so there's this trade-off between how the galaxies are moving apart from one another, because the space between them is actually increasing because the universe is expanding, versus how gravity is pulling them toward one another. And so typically when cosmologists talk about redshift, they're effectively talking about distance. There's a very close relation between redshift and distance. And it's only when you're talking about with respect to galaxies that are close to one another, like the Andromeda and the Milky Way, that when you're talking about gravitational forces or the speed, quote unquote, between two galaxies.
Yeah, and so we had a similar question, follow-up come across just now as well. With most galaxies spreading apart due to the expansion of the universe, how often is it that we see two galaxies going towards each other? I know we were on a collision course with Andromeda, so that's directly relevant to what you were just discussing there.
So going towards one another happens a lot. So in that diagram that I showed from the Sloan Digital Sky Survey, the structures that you see are what we call filaments and clusters and voids. And specifically in the clusters, there can be thousands of galaxies that kind of all live within the same gravitational influence. And so in many cases, those galaxies will be moving towards one another. Oftentimes we'll see galaxies interacting where they're in a stage where that we expect the Milky Way and the Andromeda will be in about 4.5 billion years, where they're actually in the process of merging with one another. They're coalescing to be a single galaxy. So that happens quite frequently.
Yeah, and this is something I have to deal with in my own work, is trying to separate because redshift is correlated with speed and it's correlated with distance. Right, so to try to disentangle those situations where galaxies are merging or their motions are in a lot of ways dominated by the gravitational pull they have with one another. Just trying to separate the effect of galaxies that are whizzing around one another and galaxies that are actually separated in redshift because they're in further distances. So yeah, it's a complex issue to deal with, and yeah, like these surveys are absolutely critical to kind of mapping out the universe and answering these questions about cosmology and how galaxies interact with one another. But it also brings about, we have to then take those data and massage them and try to understand kind of what's underneath the surface. So
yeah, for sure.
Well, great stuff. Thank you so much, Kyle. And yeah, so with that, have a great rest of your Thursday evening and a great rest of your weekend.
Thanks, you too.
Yeah. Okay, so next up we have Dr. Nicole Drakos, who's a postdoctoral fellow here at UC Santa Cruz. And just right off the top, she has some fascinating science for us. But I think you also have a fascinating animal, maybe, who want to make an appearance.
I have two cats, and they will probably join in during this talk. They love when I'm on Zoom, which I am a lot these days.
Great. Well, they are very welcome to the program. I didn't introduce them at the top, but certainly esteemed guests if they wish to make an appearance. So. With that being said, I think you're going to get into the mystery of dark matter.
Yes.
And Nicole is an expert in dark matter, and she puts a whole lot of dark matter into computers and watches it go. So can't wait to hear what you got for us tonight. With that, take it away.
Okay, thank you, Joe, for the introduction, and thank you everyone for coming tonight. As Joe said, I'm going to talk tonight about dark matter, which is my favorite topic in astronomy. So Kyle talked a lot about how galaxies move, and one interesting thing that you can study with galaxy motions is dark matter. And actually, one of the first pieces of evidence for the existence of dark matter comes from something called galaxy rotation curves. And the way these work are that you look at the orbits of all the stars and how fast each star is orbiting. And the more mass there is inside of the orbit, the faster something orbits. And then also the further away it is from the center of the system, the faster it orbits. So for example, the Earth, we know how massive the sun is, and we know how far away it is from the sun. So therefore we can calculate how fast it's orbiting. And you can do the same thing with all the planets, and Jupiter, which is further away from the sun, will orbit slower. And looking at this galaxy that I have here, if we calculate how fast we expect all the orbits to be based on the number of stars, we would predict something like this, where we plotted the orbital speed versus the distance from the center. So here, the orbital speed should increase, and then once you get outside of the stars, it should start to decrease, because there's no more mass as you go out further. But in reality, what you see is something like this. And this was a bit of a mystery when it was discovered. It's called the galaxy rotation curve problem. And basically what it says is that stars that are further out in galaxies are orbiting too fast. And if the only gravity is due to the stars in the system, you would expect that those would escape the system because they're rotating so quickly. And this was first really studied in the 1970s. And it was one of the original pieces of evidence that pointed towards dark matter, and what made people start to consider dark matter as being a big problem in astronomy. And since then, there's a lot of other pieces of evidence used to study dark matter. And since then, we've pretty much figured out what the universe is made out of. And it turns out that it's about 5% regular matter. And by regular matter, I mean matter that's made up of protons, neutrons, and electrons. So that's what makes up stars and planets and humans. And 26% of the universe is dark matter. And then almost 70% of the universe is dark energy. Dark energy is what causes the expansion of the universe to accelerate. It's not something I'm going to talk about today, but it's also another very interesting component of the universe that we don't know a lot about. Okay, so what is dark matter? To understand dark matter, I think it's useful to know about the 4 fundamental forces in physics, which I always think about this comic when I think about the forces. The first force is gravity, and gravity is the force where mass attracts mass. And this is what influences, for example, the orbits of stars. It's what keeps us attached to the Earth, and what causes the Earth to orbit around the sun. There's electromagnetism. So this is responsible for electricity as well as chemical bonds. So everything in chemistry is part of the electromagnetic force. Then there's the strong nuclear force, which holds together protons and neutrons. And also the weak force, which has to do with radioactive decay. So dark matter interacts through gravity, and that's how we know it's there. Because it's influencing the gravity of the stars that we can see, we know there has to be more mass there, even though we can't see it. And what's really interesting about dark matter is that it doesn't interact through the electromagnetic force. And the reason why this is really interesting is because light particles are the force carriers of this force. So since dark matter doesn't affect light particles, it makes it really hard to detect. Anything we can see in the visual light spectrum is because light particles are bouncing off and hitting our eyes, or our detectors in the case of telescopes. And if you think about most astronomy detections, they're in the X-rays or the radio waves, which are all forms of the electromagnetic spectrum. And dark matter also doesn't interact through the strong force, and it might interact through the weak force. Okay, so we know dark matter isn't normal matter. It's not anything that can be found on a periodic table. These are all made out of protons and neutrons and electrons. These all interact with light. And nobody really knows what dark matter is, but the most accepted theory currently is that dark matter is a particle that we haven't discovered yet. And it's usually referred to as a WIMP. This is a weakly interacting massive particle. And scientists are looking for these WIMPs. There's a few main ways to detect them. The first is using particle colliders. So for example, the Large Hadron Collider at CERN, what they do is they smash particles together at really high speeds and look to see if they produce any new particles. The second way that people try to find dark matter is using particle detectors. For example, SNOLAB, which is a detector in Sudbury, Ontario, and it's where they first discovered neutrinos. And these are detectors that are really deep under the ground. They're very, very sensitive, and they might be able to detect a dark matter particle if it collides with one of the detectors, which is very rare. And then the last way is called indirect detection, and this is using gamma ray telescopes in space. So earlier I said dark matter doesn't interact with light particles, and gamma rays are a very energetic light particle. But it turns out that in certain cases, it's possible that dark matter could collide with another dark matter particle and annihilate, and this would let off gamma rays. So it might be a way to indirectly detect dark matter. There is another way to study dark matter, though, and it's where we've learned actually a lot about the properties of dark matter, and that's through its effects on structure formation in the universe. So this is the area of astronomy which I am interested in, and it's what me and my coworkers at UC Santa Cruz work on. And we study this mainly through computational simulations. So I'm going to show this animation. So this is a simulation ran by a graduate student at UCSC, Bruno, and it starts off really early in the universe. And early in the universe, you have dark matter, which is shown here in purple, and you also have the gas density, which is shown in blue. And when you start off, the universe is very hot and dense, and the density is pretty uniform. But then as we allow it to evolve, sorry, the video is very laggy in Zoom. But you can see that it starts to form this structure. And this is because areas with a little bit more dark matter have more gravity. So it pulls in the surrounding matter. And then it forms this very filamentary structure. And this structure is often called the cosmic web, where you have these really bright spots of dark matter, and they're connected by these filaments. And what's important to notice is that the gas density, it looks very, very similar. And this is because dark matter, which is the majority of the mass, forms the structure, and then it causes this gravitational pull, which pulls in the gas density. And then regions where there's very high gas density, such as here, galaxies will start to form. So galaxies will trace this dark matter distribution. And one thing we want to do is we want to compare those computational simulations to observations. But for the simulations, we have these 3D simulations in time, but what we actually observe is something like this. So this is an image from the Hubble Space Telescope, and it shows a bunch of galaxies, and they're projected in 2D on the sky. But what you also have are redshifts. So Kyle talked a lot about redshifts, and this is the idea that when something's moving away from you, because of the Doppler effect, it appears redder. And the quicker it's moving away, the redder it appears. And the reason why this is a very useful thing to know is because of the way the universe expands. So one way to think about this is if you imagine the universe is a cake, a raisin cake, and in this analogy, every raisin is going to represent a galaxy. So as the cake expands, all the raisins move away from each other. And now if you imagine that you're sitting on one of those raisins, as the cake's expanding, all the other raisins are moving further away from you. And the further away a raisin is, the faster it's going to appear to move away. And this is, as I said, analogous to the universe expanding. And as it expands, the galaxies are moving further apart. And galaxies that are further away are going to end up having higher redshifts because they're moving away faster. And then also, since light travels at a finite speed, there's a lag between when a galaxy emits its light and when we see it. And therefore, the further away a galaxy is, the earlier we are seeing them. So we're looking back in time as we look further into space. So you can take the observations and build up a diagram like this. Kyle showed a really similar plot where you have, if you imagine you're right here at the point on this wedge, and you're looking out into space, you see, so this is the angle that you're looking at, and then you can find the redshift for each galaxy. and based on the redshift, put it on this plot. So the higher its redshift, the further away it is from you at the center. So this is what we see in observations. And then if we compare that to what we'd expect from our simulations, you'd get something like this. And as you can see, they look very similar, which is great news. It means that the physics we use in our simulations is probably really close to what's actually happening. It means our understanding of how things form is quite good. And one thing that you can do is you can run a bunch of different computational simulations. You can change the amounts of dark matter. You can give the dark matter different properties, so change how quickly they move around. And then you can predict what sort of distribution of galaxies you get and compare those to observations. And you can use that to start to get an idea of the ways that dark matter behaves in order to be consistent with what we actually see in the universe. So in summary, the universe is filled with something called dark matter. It's invisible, but we know that it's there because its gravitational pulls on stuff we can see. The most accepted theory is that dark matter is something called a WIMP. So this is a weakly interacting massive particle. There are different ways that scientists are looking for dark matter, such as particle colliders, particle detectors, and also through dark matter annihilation signals and gamma ray telescopes. But another way to try to study dark matter is through computational simulations of how the universe forms, and then looking at that structure and comparing it to observations. Okay, thank you very much for coming today and listening to our talks.
Awesome. Thank you so much, Dr. Drakos. That was fascinating, as I knew it would be. So just to kick things off, back to the cake. We have a question from our YouTube live. Why does it have to be raisins? Why can't it be chocolate chips?
It could be chocolate chips. Yeah. Okay.
Maybe this,
I feel like the traditional argument is with raisins. I don't know why though.
Maybe this will be borne out in some of those experiments you were talking about. Maybe at the Large Hadron Collider, they will.
Maybe it's because chocolate chips melt. I don't know.
It's
like fuzzy dark matter or something.
Right, and raisins might hold their structure. Good. And so as a follow-up question, if I'm sitting inside the cake on a raisin, can I not eat the cake?
I think you're taking the analogy a little too far.
I don't want to imagine myself on a raisin in the cake if I can't eat the cake.
You can eat the imaginary cake if you want.
Okay, great. Glad we got past that little logical paradox. I'm now open to your science. No, just kidding.
Thanks, Joe.
We actually have a serious question, and it's a good one. And so this is, what are your thoughts on the recent possible detections of axions by the Xenon experiment?
I haven't really been following that closely, but my understanding is that is, so that's a particle detector, like I showed the Snow Lab as an example. And they did find a detection, but they're still trying to determine whether or not it's a real signal. So the problem with detectors like that is they're looking for such a small signal. They're very, very sensitive, and therefore they're also very sensitive to noise in the experiment. So I think it'll take a little bit of time to know whether or not they actually detected anything. But if they did, that would be very interesting.
Okay, yeah. And so this is something that actually you could help me understand a little bit better. I see these papers in the archive talking about different forms of dark matter. So there's axions are kind of maybe one candidate. Is that right? And so, and you alluded to how you can change the properties of dark matter in your simulations. So maybe if you want to just take a couple minutes, could you kind of give us a sketch of maybe what different behaviors these different sort of flavors of dark matter might possess?
Yeah. So one thing that's been determined is that dark matter is cold. And so in the simulations, you can change, for example, how quickly the particles move around early on in the universe. And so there's a model of dark matter where it's hot. So these have less mass. They're moving around really quickly early on in the universe. And what happens is they're moving around so quickly that they wash out all the structure. So they would actually, so galaxy size dark matter wells, they would get destroyed. So you wouldn't end up with anything on the scale of a galaxy. And to get the really sort of clumpy structure we see, dark matter probably has to be cold, at the very most like a lukewarm. So that's one example of where simulations have really constrained the properties of dark matter.
Yeah, so so there's this cold dark matter, and so do we know? So I guess because we know dark matter is cold, then hot dark matter is probably ruled out.
Yeah, and it does give you a mass and energy constraint on the particle. And really a lot of the candidates that you have for what dark matter particles could be come from other areas of physics. So for example, the axion, I forget why that's proposed, but these are particles that came up in other areas of physics and particle physics to explain something. And they haven't been detected, but somebody else has thought they had to be there for some reason. And they might also work as dark matter.
Gotcha. So maybe they fit the bill in terms of mass and energy,
Mm-hmm.
and they bring along some other properties, perhaps. That
Right.
could, make for detection.
Yeah. So right now, cold dark matter is the predominant theory, but there's also somewhat more exotic ideas that are really popular right now. So self-interacting dark matter and fuzzy dark matter are kind of the two main ones. There's also some arguments for warm dark matter.
It seems like from the observational standpoint, so people like yourself, you can inject these different properties in the simulations, and you can see the structure that emerges. So observationally, it seems like the types of surveys that Kyle was talking about earlier, the Sloan Digital Sky Survey, and just these big maps of galaxies in the sky are pretty key to distinguishing between these various models of the nature of dark matter. Are there any upcoming experiments or surveys that you're particularly excited about that maybe you could look towards and think, okay, well, this is going to be maybe a step forward in terms of constraining my science?
Well, so one of the main constraints for dark matter is actually CMB experiments. So looking at the cosmic microwave background, which is a leftover radiation from earlier on in the universe. And those experiments have gotten better and better and better. But there are some what are called tensions that have come up where constraints from CMB experiments are not quite in agreement with other experiments that look at things more locally in the universe. And this doesn't directly relate to dark matter, but one of the things that there's a tension in is how fast the universe is expanding. So to me, a really interesting cosmological problem is to try to pin down why there's that discrepancy. And for example, W1st, which is coming up, will look at the expansion history of the universe. And maybe it will tell us a little bit more about how fast the universe is expanding. And if we can sort out that problem, maybe that will tell us something a little more interesting. As far as detecting dark matter, I think it's more the particle colliders and particle detectors that would be more fascinating if they discovered something, because that would be, if they discovered a signal and were able to say that signal was real, then that would solve this mystery, which I think will happen in our lifetime.
Wow, very cool. So we've sort of moved beyond just the maybe the more indirect indicators or measurements, and so now we're actually able to maybe make experiments here on Earth that could. I
guess the one thing is, as detections get more and more sensitive, for example, like looking at gamma ray signals, you can rule out different energies and masses of dark matter, because you would have detected a signal by now if they were that energetic. So one thing I'm really interested in doing is studying that dark matter annihilation signal. So looking at mergers of what are called dark matter halos. So those are the really dense parts of the dark matter, and then trying to figure out how they change, because in those really big computational simulations, you run into computational problems where the amount of computational power you need to actually get the answer in detail is more than we can do. So we want to make sure we're doing a very careful job so the constraints that we have on what the signal should be are accurate.
Okay, yeah, cool. So we'll certainly keep we'll wait with bated breath to hear what comes out of those experiments. One more question coming from the YouTube live chat, and that is dark matter something that can form a solid? So do we have an idea maybe of what phase?
So solids are usually because there's chemical bonds between atoms, and dark matter doesn't form chemical bonds. It's what's called collisionless, and this means that if two dark matter particles pass each other, they don't really affect each other at all. They're not going to bind together. So I guess the answer is no. Due to our current understanding, they will not form solids.
Okay, well, there you have it. Thank you so much, Dr. Drakos. This has been it's been fantastic. Have a great rest of your evening. Enjoy NEOWISE if the marine layer permits it tonight.
Right, bye. Thank you, Joe.
Have a great weekend.
Everyone else.
Yeah, take care. Okay, and so we are very rapidly approaching the end of our program tonight. I did want to introduce a very special guest we have joining us. This is Alexandra Mannings. Alexandra will be the host for Astronomy on Tap, likely these virtual online editions coming up for at least the next few months. So I want to say hello, Alexandra. How are you?
Hello, I'm good. How are you?
Oh, doing great, and doing better, knowing that that you're going to pick up the Astronomy on Tap host role and carry it to spiraling new heights, I'm sure. So tell us a little bit about yourself.
Yeah, so I'm first of all really excited to start up and take up the MC position for Astronomy on Tap. I've been involved with the event since about November or December of last year, so I'm really excited to be more involved. I'm just finishing my first year of grad school here at UCSC, and I am studying fast radio bursts, or FRBs, and looking at or studying the galaxies that are hosting these FRBs. So I work in the same group as Joe, so we are sad to see him go, or to see you go. Yeah, so right now just looking at or analyzing some images from the Hubble Space Telescope to learn more about some hosts of FRB events. So really having a good time and looking forward to what the next few years hold. So
awesome. Yeah, and I have to say, you're working in just one of the hottest fields in all of astrophysics right now. So that must bring with it a lot of excitement in and of itself. So yeah, I'm delighted to see how where the direction you take things here in the next few months, and I'll be tuning in from southern New Mexico. Good. And looking forward to it. So yeah, have a great rest of your Thursday, and enjoy the evening. Enjoy NEOWISE, and yeah, it looks like maybe the marine layer is going to hold off. We'll see.
Yeah, it's looking really good right now. So keep my fingers crossed. All right. Have a good night. Thanks.
Thanks again, Alexandra.
Bye.
Okay, and that will about do us for tonight. I will be signing off, and as one of the co-founders of Astronomy on Tap Santa Cruz, I will be moving to a faculty position at New Mexico State University coming up in the fall. And I want to say thank you to all the wonderful people I've had the pleasure of working with over the past 3 years, getting Astronomy on Tap Santa Cruz off the ground. and making it what it is today. We couldn't have done it without you. So I know Alexandra is going to be great. And Ann Datillo, who is with us, might as well go ahead and turn on your video for a second, Ann. I'll put her on the spot there. Hello. So yeah, thanks to Ann. She's going to be taking over technical coordination, production of the Astronomy on Tap online editions coming up here in the next few months. And yeah, like I was saying, I'm looking forward to tuning in from New Mexico and checking out your all shows. I'm sure there's some fascinating stuff coming up. So thank you. And yeah, thanks again to everyone who's been involved. Thanks to New Bohemia, Santa Cruz Mountain Brewery, Xavier Prochaska, who's been a faculty mentor for AOT Santa Cruz. And most of all, thanks to all of the people who've been coming out to our events. I hope that we'll be able to do it in person very, very soon. So have a great evening. Like I told everyone, enjoy NEOWISE, and until next time.